All right, welcome. So in this video, I actually want to practice using our recursion tree technique to come up with a good guess for a bound on a recurrence relation like the one I have here. Now, some of you might already know about the master theorem, and if you don't, go ahead and check it out. Got a couple of videos about it as well. But we could use the master theorem on this and cheat and just say, hey, I know what the bound is. And in fact, when I'm practicing my recursion tree technique or the repeated substitution technique, I'll often use recurrence relations like this where I can cheat with the master theorem, because then I can go look and see what the answer should be. So if I go and do my math and I get something different, I can say, oh, looks like I made an error, and I can find that error. Otherwise, I can check it. If I got the same answer, then I can be confident that I probably did most of the steps correct, or maybe all of the steps correct, hopefully. All right, so let's practice here today the recursion technique. Now, some people use the recursion technique to construct proofs by construction, which works if you do all the steps very well, or you make simplifying assumptions to make each step a little bit easier. But I usually use the recursion tree technique as a guess step that I usually later prove with another technique like induction. And so what that means is when I use recursion tree, I allow myself to do little tiny approximations, hand waves here and there, blur my eyes, shove things under the carpet, little tiny ones, like ignoring a +1 or a -1, a little thing here or there, if I know it's probably not going to make an impact to my guess at the end, because at the end I'm just guessing. And so I might do that here today. And in fact, I've already kind of done one without thinking. You'll notice that inside my recurrence relation here, I do not have a floor or a ceiling. I've just got n over 3, and that's fine because I've kind of already thrown it away. I've just pretended it's not there. And so if you had a floor or a ceiling in yours, you might throw it away same as me. If you have a -1 in there, careful. I wouldn't necessarily throw that away, because you might destroy your recurrence relation and how it's defined, but you might want to throw a floor out of there, as I have. But let's do the recursion tree technique. This one is just what I sometimes call, it's not really a tree, it's what I call a stick or a branch. It's just one long connection of nodes, or in this case, recursive calls. But I usually want to keep track of a few things about each level of this tree, and each level here. Well, why don't I give them a name? Why don't I call them levels? Okay, what level are they? And often, to be useful in my math and a little bit later on, this is something I get out of experience. I usually start counting at 0 for my level, okay, and then 1, and then 2. And as you know, sometimes computer scientists, we count from 0, other times we count from 1, okay? It's helpful in our math in this case. So we've got our level, and then I might also keep track of my size. Now the size of my recursive call initially is this one here, which almost without fail is an n. At least in the examples I'm used to using, it's always n. Okay, you can imagine a recursive relation that might have multivariables here, more than one variable. In that case, like an n or an m. I could imagine that too, but often we try and simplify it down to this. What about the size on the next level down? What happens in the next level down is determined by what we have going on inside of our t relation here. Now, most of the examples that we use in recursive analysis will often split our list into 2, or in this example, it looks like we'll split it into 3, and so we get this sort of division going in there. And this is usually why we might need a floor or a ceiling operation, doing a little bit of extra work there, turning this argument into an integer as we expect it to be. However, we also might encounter the kinds of recursive relations here where we might have an n minus here, and this would be where we would have an n minus here instead. So sometimes we go down by 1 every time. This is a common recursive algorithm design as well, is to just remove one element at a time, in which case you get n minus 1, n minus 2, and so on the way down. In this case, we had n over 3, so if we want to, and I'm actually going to sort of jump into trying to identify a pattern here, we're actually going to get n over 3 squared here. And again, if you're following, you can see maybe why starting at 0 was strategic here. Okay, so these are the sizes. I haven't got all the way down, but we're trying to get these identified. I'll usually go 2 levels down like this, and maybe more if I need to, but this one I think might be simple enough. The other thing I want to do is I keep track of a couple other things. Now, I'll keep track of the number. This is the number of nodes per level, and because we've got this stick, this branch over here, and also you can see that out here, there's a hidden little 1 out front there that we didn't really notice because it's hidden. But that says how many nodes on each level? 1. Well, on the next level, it's still 1. We only make 1 recursive call and so on. And so often in these cases, which while we've been looking at divide and conquer, this is an example of what we sometimes call decrease and conquer, where we only make 1 recursive call on each step. In those cases, this column, I might ignore it. I might not leave it in there. But in the general recursion tree technique, we do want to know the number of nodes on each level. And so I'll leave it in there. Why not? 1 on each level. What we do want to know then is the cost. And I'll be a little bit more careful here. Cost per node. Because this function here, which we sometimes call f of n when we're talking about these recursive functions, this function right here is what determines the cost per node. Okay, in this case, I've kind of strategically put 5n in there for a reason instead of just 5, because I wanted it to depend on n, so I could show one particular feature that is important, is that as we go down, as the size of our nodes decrease, the cost will go down as well. So on the first node, we had 5n. That's because when the size was n, the cost is given by this function here. But when our size is n over 3, we need to plug in that n over 3 here for our n. So that gives us 5 n over 3. And usually when I'm doing this, I'm going to leave this 5, whatever it is, out front alone. Even if it canceled, say we had n over 5 here and it canceled, I might not cancel it. I might leave it alone, because remember, the goal here is to find a pattern. We're trying to find a pattern, because on the next level here, I might have n over 3 squared, and I might want that 3 from the last level so I can see that pattern as I go down. Now, why did I need to know the cost per node, and why was I counting how many nodes? Well, because usually I want to know the total cost of the whole level. So I'll usually just call this the total cost, but if I want to stress it, maybe I'll say of the level. Okay, now that's terrible. Total of cost level. Well, that doesn't make sense. Figure it out yourself, I guess. Okay, total cost is usually what I call it. But how do we get this level here? We multiply this column by this one, because this is the number of nodes. And remember, for this example, it's just 1. We'll do another example in a second. This one here, though, this one is the cost per node. So number times cost, multiply them out. Well, it's 1 for our number, so we're not getting anything special here. We get 5n over 3, 5n over 3 squared. Now, the purpose of doing this math in this recursive tree technique is to sort of scooch our way down and get down to a level that I usually call level I. So some other level down here. On that level, we'll also have 1, because it's 1 all the way down. But I want to find a pattern now. And in each of these columns, sometimes the patterns are easier to find than others, but ultimately it's this pattern that we're trying to find, the cost of each level, because we'll add them all up to get the cost of the whole algorithm. So we'll continue here. This pattern, again, I was already trying to write things to stress the pattern. We can see this value. Well, if we're on level I here, then we must have n over 3 to the I as our size, Okay, our number, well, the pattern is pretty easy to see there. It's 1. Okay, it's going to be 1 all the way down. Cost per node. Okay, well, good thing we put some effort into making sure we plugged in the size to the cost per node to make sure we got that right. So that means if we copy that pattern down here, we're going to get 5n over 3 to the I. Okay, and again, multiplying that out isn't going to change anything for us. 5n over 3 to the I. Now, I'll usually focus in on this node. This is really all the work we've been doing is to focus on this one, except there's a little bit more that we need to do. We're going to continue down. Now at some point, if we keep dividing by 3, dividing by 3, dividing by 3, we're eventually going to get here to our base case, 1 or less, or 0. If we had floors or ceilings, we don't, I haven't stressed that, so I'm sort of ignoring that we do have to round this off in some way, but eventually we'll get down to 1 or 0, and then we're going to have 6. We're not going to have any more recursive calls. So I'm going to draw something now. I'll say we've got a little square. That's our terminating our leaf in our recursive call. Okay, instead of doing another recursive call, we kick out something. Okay, on this level, I don't know what this level is, but I'll usually give it a name, and I'll usually give it the name k. And I have to solve for k in a second. We'll get there in a second. The size of this level, there's, what I write here, I'm often not 100% sure, but we know if we're on the last level, the argument I just said is that level is where my n has become less than or equal to 1. So sometimes I want to write 1 here, but maybe let's just write less than or equal to 1 here. Okay, this is going to be the size, and all that's important about that size, again there's only 1 on this level, is the cost is now 6. This is the other term that we actually want. Actually, we're going to go ahead and multiply 1 times 6 gives us 6. These are our two terms. Now the reason these are the ones that are important is I want to now add this all up. So we want to add these all up. Okay. If we're doing recursion tree technique and we did this inside, say, an Excel spreadsheet, we just punch sum at the bottom, there we're done. Okay. Well, that's how we do it in Excel. How do we do it in math? Well, to punch sum just means, there you go, I punched the sum. Okay. But unfortunately, we've got two different expressions here, and that's why I've sort of squared off 2. The one on the bottom always stands on its own. This is the base case, the last level. The last level always is just its own expression. Now I've got the sum here. I'm going to put the 6 in front to say that it's going to be 6, that last call costs us 6, plus whatever the cost of the rest of these are. Now, the reason I squared this middle one here, this level I, is because it's written in terms of I, not a constant like up above. It's general, it expresses the term generally, okay? Meaning it expresses it for every level. Meaning I can write that right here, 5n over 3 to the I, as long as the sum I'm summing over is I. And then I just need to decide what are the two bounds for my I here. Well, I've got I equals, here, now this is where I jump into this level here, my level column. That's where I lives. I started at what level? Level 0. What level did it stop at? Now here, sometimes if we're sloppy, we say K. Now here's one point where I say, hey, if you're guessing like I do with this is sloppy, but it's fine. Your guess will probably work out exactly the way you want it. But it's not exactly true because remember, this last level is different. It's 6. We don't sum over this term on the last level. We get down to k minus 1. That's the last level we do it on. So again, that minus 1, you forget it. Probably not going to affect your final answer, but if you want to be exactly precise, sometimes we use this as part of a proof, then we would want to make sure we get that exactly right. We don't want to mess it up. Okay. All right, now continuing. Usually if we can get this far, all the effort that we have to do left is figure out this sum, and this sum is usually it's going to be one of 3 types, which is if we're working with a master theorem like a recurrence relation, which is probably 90–95% of the time in computer science, in which case we end up in 3 cases, and I'll just maybe go through that one of these cases right now, which is we're going to have to factor out some of these values, and when we do factor out the ones that don't depend on I, we'll be left with something inside here. Let's do one step here. So we'll do 6 plus, what can we factor out here? We got I here, we got 3 to the I, we can't factor that out, but the 5n, that factors out. We get I equals 0 to k minus 1 of 1/3 1/3 to the I. Now the important thing about this sum, usually if we've done our math right as we've done here, you're going to get something probably that looks like this, something to the power I, and there's going to be a couple possibilities here. In this case, we've got something less than 1. Okay. We could also get something here that is equal to 1. That's when we might actually have two terms, like earlier over here, we might on the top have a 3 to the I in there. Down on the bottom, we had a 3 to the I. They could cancel out and give us 1s. So sometimes we get a 1 there. Okay, when we get a 1 there, we know what to do. We just get that k minus 1 popping out. That's pretty easy, right? And then the other possibility is when they cancel out, instead of getting something less than 1 like this, we get something greater than 1. And again, we can use a simple formula for that. Now, here's an important thing is, so let's take a look at a sum here. I guess I'll leave it at k minus 1 for now. We have a to the I. Let's see if we can remember this. Now, we can write this formula, and you can, this is sort of a, if you're not really sure how to do this, go look it up. You might find in your book, in the textbook, there's a formula for this, and that formula says something like this. It says, well, it's going to be a to the k minus 1 all over a minus 1. And if we're kind of just blindly plugging numbers in, then we'll get the right answer. We'll get a answer. It might not be the right answer in the sense that it might not be in the form that we're necessarily looking for, because sometimes when I do something like this, the next step that I'll see a student do is this. They go grab this formula and they go say, well, this then is 1 over 3 to the k. I'm plugging in my a. This is my a, right? We kind of have the right formula here. We have minus 1 all over, again, 1/3 minus 1. Sometimes students will get it this far and kind of leave it like this and say, well, I don't know what this is, and I don't blame you. This is kind of a weird thing to write down. Partly because when we minus the 1s off here, this turns these both into negatives. And if we cancel them out, for instance, it's easier on the bottom to see 1/3 minus 1 gives us negative 2/3. Well, it turns out the top is also a negative. We could cancel them out. We could get something a little bit better than this. We could simplify this to get it better than this. But the fact is, we probably don't want that. This is, at least for me, who uses this as a guess, I use another trick here. So here's the other trick that I'm going to show you here. And at least this one calls out to a Greek philosopher, Zeno. I think I've probably done this in one of my other videos too, but I love this story, so I'll continue it here. So let's talk about Zeno. And actually, Zeno didn't talk about this particular sum with 1/3. Let's see, I guess I could do it with 1/3 too. Zeno is a clever guy. I'm a clever guy, so I can do it too. So Zeno was an ancient Greek, and those ancient Greeks, they loved lots of cool things. They loved philosophy, and I love philosophy too, and they loved math, and they loved geometry. And so Zeno came up with this fun sort of philosophical thought experiment. You can imagine your Greek friends. This is a terrible picture. Please believe me when I say here that what I have here is a turtle or a tortoise. Turtles, of course, are never going to be racing anyone with their flippers. Tortoises are the ones who race on land. And of course, this here is Achilles. And Achilles, everyone knows, is a famous Greek hero who had winged slippers. Oh, I probably got this wrong, so now I'm drawing wings on slippers, so I got this all wrong. But Achilles, famous guy, known to be fast. At least I remember this much. So we've got our famous Greek hero, known to be fast, I think played by Brad Pitt in a movie one time, and a tortoise. And the idea was, this is sort of like the tortoise and the hare myth that you've probably heard before. Xenos Paradox said, hey, what about this idea? Imagine that we were going to have a race between Achilles and the tortoise, and let's say, actually, they're going that way because of the way I've drawn it. But we give the tortoise a head start. That's what Zeno said. And he's going to make this following argument. He says, the reason, or he says, Achilles will never be able to catch the tortoise because, he says, Achilles must make infinite steps. And here's his argument. He says, first, before Achilles gets to the tortoise, he must reach 1/3 of the way. Okay. Xeno's original one had 1/2, but we're going with 1/3 because 1/3 is what we got up here. Okay. And he says that's one step, or at least this chunk here is one step. And then he says before he gets to this point, 1/3 of the way there, he has to get 1/3 of the way there, which is 1/3 squared there. And then before he got 1/3 of the way there, he had to get 1/3 of the way there, and 1/3 of the way there, and 1/3 of the way there. And you can see by the infinite lines I'm drawing here that there would be infinite steps in between Achilles and the tortoise. Now, if you believe Zeno, what you believe is this. You believe that the sum of I equals 1 to infinity, because he said there's infinity of these steps, of the first step was, let's say, 1/3. I'm messing it up because I drew pictures and this is a fun picture, but we're looking at this sum here. So let's say we had this 1/3 plus 1/3 to the power 2 plus 1/3 to the power 3 plus 1/3 and so on, all the way to infinity. Now ours didn't go to infinity, ours went to k minus 1. But what Zeno said is if you summed up all of those things, this adds up to less than, at least in our case here, 1. Now, our example up here is starting with 0, not 1. So that means we have one extra term. Well, 1/3 to the 0 is 1. So actually, if we add this, if we change this to 0, change it to 0, this one becomes a 2. And in fact, if we change the 3, the 1/3, to a 1/2, then this sum all the way to infinity is exactly equal to 2. Okay, if you go all the way to infinity. Now again, why all this extra aside talking about Zeno and his paradox? The paradox was, of course Achilles can catch the turtle. Hopefully we all figured that part out. He, in ancient Greek times, he thought this was a clever puzzle. And it was a clever puzzle because it identified this fun summation that we were looking at here. But our purpose for looking at it was to say that, look, this sum here, if we plug in this, even though it's still going to have this weird k in here, what we're going to see is this is going to be less than or equal to a constant at least. 2 by my argument over here, but some constant. And in fact, I think for our example of 1/3, we get 1.5 instead of 2 if we went to infinity. Either way, it's a constant. You can double check that yourself if you want to do a little extra math on the side. But this constant here, we can just plug it in up here, and we can say this whole sum is just less than or equal to some constant. So what were we doing in our math here? We had 6 plus 5n times a constant. We could actually lump it into our 5 there and just call this c times n plus 6. Or maybe c prime if I've already labeled a c here. But in any case, we can see this would be a theta n algorithm if this was our actual recurrence relation. And again, run this through Master's theorem and you're going to quickly see, oh yeah, this is theta n, so check, we did it right. Okay, I think this is probably long enough for this video. I'm going to probably add another exercise or two with the recursion tree technique. But thanks a lot for watching, and we'll see you in that next video.